So, in this unit, we are going to start looking at gases. So, we have been really focused on um, solid things or things in solution, in aqueous solutions. We're looking at reactions, um, but we also saw that things would release gases. So, now we're going to look at what happens when we trap these gases in containers. How do these gases act? What are some rules for them? What are some things we can predict because of them? And so we're going to take a look at that. So the first thing we're going to look at is our kinetic molecular theory. And this theory tells us, hey, if gases were ideal, so if this was an ideal world, which we know that we don't live in an ideal world, but if it was an ideal world where, we can control pressure, we can control um, temperature and all this stuff, then gases will act this way. And so we're going to take a look at that today. So the first thing we need to understand is we need to understand how gas particles interact with each other. And what's happening is that when they're inside of a container, they're moving around and they're just kind of going anywhere they want to go, but they're hitting each other. They're colliding with each other, they're colliding with the sides, and that's producing an energy, a kinetic energy. And that's what we're going to be focused on and looking at today. Okay. This energy, when it's being when it's there, it doesn't change when they hit each other. So we're going to talk about how when they collide, the energy doesn't dissipate. It just goes in different directions. Okay, so you can see here how they're kind of colliding with each other, things like that. So the kinetic theory, there have different things you can kind of see here. You can see the energy as it's bouncing off, and every time it hits, we leave little marks. Okay, we can see this path. They're very random, things like that. Okay, and here you can kind of see the gas molecules. Here is bromide gas um, in a container, and it's just moving around very quickly, and that's what's kind of giving it that color, that bromine color of brown. Okay, normally we can't see gases, but some of them do have some colors to them, depending on what we're seeing, and that's based on the energy. So first thing is particles are in constant motion. They're hitting the walls. They're causing this energy. Okay, so the kinetic molecular theory, okay, has 5 postulates, okay, or 5 pieces to it. Okay, and these 5 pieces are going to explain why gases behave the way they do. Why do certain gases rise? Why do certain gases get cold? Things like that. It deals with the ideal gas particle. Okay, now of course you're going to see videos about real gases at some point, but we're going to deal with just the ideal. Again, if all the conditions are great, this is what would happen. Okay, so here are my components of my kinetic molecular theory. Okay, first off, that gases are made up of tiny particles. So they're made up of atoms or molecules. Atoms, if they're single, so like for instance, helium, okay, would be a single atom. You can have single atom of helium because it doesn't bond with something, or you can have molecules. So for instance, oxygen, because it's diatomic, has to be partnered with somebody. It'll be it'll be a molecule because it'll be two oxygen atoms connected to each other through covalent bonding. Okay. These particles are super small. They are so, so small. Okay, think about it. Our atoms are beyond microscopic. Okay, and so because they're so small, okay, the distances between them, the distances between them, um, it makes their volume, okay, the volume of these particles to be almost zero or negligible. So really, in essence, what this is saying is that because the particles are so small, there is no volume. Gases have no volume. Okay, gases have no volume in the particle themselves. Now, when you put a bunch together, you can fill up space. Okay. Again, particles are in constant random motion. There is no fixed track. So what's going to happen is a particle is going to go, it's going to hit another particle and bounce into another direction. Okay, that's what you were seeing earlier with the collision. Okay, that collision is elastic, which means that it's going to, the energy is just going to continue, okay, but they're going in random motion. They're colliding with walls of the container. All of these collisions are what's causing pressure, okay? So the collisions are causing the pressure, okay? And they're being exerted. So that's what the causing the pressure exerted by the gas. Gases don't have anything to attract or repel each other. So we're saying that they have neutral charges, okay? So they're not going to be attracted to each other, which means they're not going to stick together, okay? And they're not going to repel each other, which means they're not going to go apart before they actually hit each other. So gases will interact with each other, but they won't stick together and they won't repel each other away, okay? So that, and then that repulsion is, the reason that repulsion thing is important is, remember, they want to be in constant random motion. And so if you're going to repel, then that's going to cause that motion to not so much be random because you're trying to avoid things. And then finally, the average kinetic energy of your gas. Okay, remember, there's a lot of energy happening. So kinetic energy is energy on the move. Okay, it's directly proportional to temperature, specifically in Kelvin. And we're going to talk about Kelvin temperature tomorrow, but it's directly proportional. So the higher the temperature, the more energy. That's what it means to be directly proportional. So if you go up, the temperature goes up, okay? If your energy decreases, your temperature decreases. That's what that means to be directly proportional. So whatever one does, the other one does the same thing. Okay, so those are our 5 postulates, okay? So again, as our temperature increases, our kinetic energy increases, okay? Okay, so remember, they're so small they have no volume. They're in constant straight line motion. That was the other thing. When I'm saying random motion, they're in a straight line motion. Okay, they're going to experience elastic collisions, which means when they bump into each other, the energy is not going to get lost. Okay, they're not attracted or repulsed by each other. And then again, that average kinetic energy is proportional, okay, to the absolute temperature, also known as Kelvin temperature. Okay, so this is the big thing about elastic versus inelastic. Okay, so elastic means that the total energy is conserved, it doesn't change. So as the white ball hits the black ball, okay, that energy is going to continue through. And so the black ball will keep going at the same speed as the white ball hitting it when it hits it. An inelastic collision means that there's going to be a change in that. So if the white ball hits the black ball, maybe they both stop, or maybe the black ball doesn't really move anywhere. Okay, so that's the difference. Okay, elastic means that the energy is going to keep going. Okay, it might just go into a different atom. Okay, in this case, the energy from the white ball will move into the black ball and keep the black ball move forward. Inelastic means that the energy in the white ball, when it hits the black ball doesn't move. Okay. Okay, and you can kind of see that there. Okay, so this is an elastic collision. So you see how the white ball hits and then the black ball moves. Okay. If we're looking at a model behavior, all of our collisions have to be elastic. So that's the assumption we're making. Okay. And so we're kind of, I think this is more of a practice thing. We don't really have this right now. But you can kind of see how this would work. Again, are all of our class be elastic when we actually get a chance to kind of see that. So we're going to press that. Okay. So again, our particles in the ideal gas have no volume. They have elastic collisions. They're in constant random straight line motion. They don't attract or repel each other. And they have an average kinetic energy that's related directly to Kelvin temperature. So as one goes up, the other one goes up. Okay. And this is just showing you the speed at which they're going, okay, as they're moving through. Okay, so that's the kinetic molecular theory in a nutshell. Nothing too much to it. We're just seeing how all of these kind of interact.